In this video, we're going to expand on what we looked at in our previous video on electromagnetic fields. And we're going to look at magnetic fields in a bit more detail. And we're also going to look at solenoids, which are an example of an electromagnet. But before we get on to that, I want to look at even just the most basic magnet, a bar magnet, like the one in the diagram below. We know that a magnet obviously has magnetic properties, and we can represent those magnetic properties by a magnetic field. And the way we draw a magnetic field for a bar magnet is by drawing field lines that travel from the north to the south pole. And so we can draw them on something like this. We have lines that travel from the north to the south pole, like so. And a few properties of these field lines are firstly that they have a direction, and so we said that the field lines are going from north to south, and so we should make that clear on our diagram. Another thing that should be true for our field diagram is that because the field gets weaker as we get further from the magnet, the spacing between the field lines should get bigger, which isn't necessarily perfectly the case for my diagram, but I've done my best here. So the spacing should get wider and wider as we get further from the magnet, and that's meant to represent the magnetic field getting weaker as we get further from the magnet. What we can also see from our diagram here is if the closeness of the lines represents the strength of the magnetic field, then the strongest magnetic field is going to be found near the poles of the magnet, where these lines are the most concentrated, the most dense. So I want to mark a few things on our diagram here. First of all, the proper term for these lines is something called magnetic flux. And magnetic flux is represented by field lines, but we can make a note of it here. So magnetic flux is the proper term. And usually we give magnetic flux the Greek letter phi as its symbol, which is almost like a capital I with a circle inside of it. And magnetic flux has a unit. It's measured in Webers. Often shortened to just WB, but we measure magnetic flux in Webers. The next thing to think about on our diagram is area, because we've mentioned that there are some areas of our diagram, for instance, when we're far away from the magnet, where the field lines are quite sparse, whereas there are some areas on the diagram where the field lines are quite compact, and that obviously has some kind of implication on the strength of the magnetic field. And so what I want to do is I want to try and represent area on this diagram. If we imagine that we have an area, for instance, I'll try and draw a sort of 3D representation of an area, and I'll call it A. Well, this particular area that I've drawn has only one field line going through it. Whereas if I draw the same sort of area, even if I imagine it's the end of our bar magnet, I can try and represent the area of the end of the bar magnet there. And we can see that there are 6 lines of magnetic flux going through that area there. And so the area has an implication on something called the magnetic flux density. And magnetic flux density, we give the letter B. And the formula for B, the magnetic flux density, is simply phi over A. So it's the magnetic flux divided by the area. So for instance, in our top area here, we have very little magnetic flux going through a given area. And so B, the magnetic flux density, is going to be very low. Whereas in a different area, I have quite a high magnetic flux divided by roughly the same area, and so the magnetic flux density is going to be high in this instance. So I could mark on my diagram here that this is an example of low B, and this is an example of high B, high flux density. Let's have a go at trying to work out the magnetic flux density at the end of this magnet here. And let's say that we know that the magnetic flux in this instance is 500 microwebers. So I'll make a note of that, and we'll say that phi is 500 microwebers. And let's say that we know that the area of the end of this magnet is 150 millimeters squared. So 150 square millimeters is our area. And what we want to try and do now is work out the magnetic flux density of this area here at the end of the magnet. So to calculate this, we're going to use our formula B equals phi over A. And in this case, we know that phi is 500 microwebers. Now we know our standard prefix micro represents 10 to the minus 6. So in our formula, we should say 500 times 10 to the minus 6 webers over the area, which is given in millimeters squared. Now our SI unit is meters. Something to be careful of here is that although there are 1,000 millimeters in a meter, there are 1,000,000 millimeters squared in a meter squared. Because if we think of a meter, we have, imagine a meter squared, 1 meter by 1 meter. There are 1,000 millimeters by 1,000 millimeters along the sides. So that gives us a total of 1,000,000 square millimeters if we multiply them together. And so we've got to be careful when we're converting our area, 150 millimeters squared, into meters squared. So because there's 1,000,000 millimeters squared in a meter squared, we have to use the 10 to the minus 6 in this instance as well for a millionth. So we'll say 150 times 10 to the minus 6. And if we cancel those 10 to the minus 6's out, because we've got a 10 to the minus 6 on the top and on the bottom there, we're left with 500 over 150, which gives us 3.33. Finally, the unit of magnetic flux density is Tesla. So we give it the capital T for Tesla. So B is magnetic flux density. And it's measured in Tesla, T-E-S-L-A, or just a capital T for short. In a previous video, we've talked about how a conducting wire produces a magnetic field when a current flows through it. And what we can do is we can take advantage of that by coiling a wire into what's called a solenoid. And what we find is that when we have a coil of wire, like the one in the diagram here, and we pass a current through that wire, we see the same sort of shape of magnetic field as we would see in a bar magnet. And so we get a magnetic field produced. Let's have a closer look as to why that's the case. In our previous video, we looked at the symbols for conductors with currents travelling away from us and currents travelling towards us. And what we can imagine is if we kind of take a cross-section of the coil that we've seen on the previous slide, we might see something like this. And what we have is, along the top there, conductors with currents travelling away from us, and then looping back round along the bottom there, we have those currents travelling back towards us again. And so we can think of a coil as a combination of these currents travelling away and towards us. And what we spoke about in the last video is that currents travelling away from us produce a clockwise magnetic field. And so what we can draw on here is magnetic fields. I could draw them individually around each conductor, but what we talked about is that these magnetic fields sort of group together. And so what we'll see is something that looks like this, where we have a magnetic field produced, and it's in a clockwise direction in the case of a current travelling away from us. And so what we have is, along the top here, we have a magnetic field produced in that clockwise direction, and along the bottom here, we have a magnetic field produced in an anti-clockwise direction. And what we can see is, if we kind of expand on this idea, we'll see that we have this kind of similar magnetic field produced as a result of the behaviours of these two sets of conductors. Based on this, we can calculate a new parameter which is called H, the magnetic field strength. And it's measured in this unit at the end here, amp turns per meter, which will become a little bit more apparent in just a second when we look at the formula. So H is a measure of the strength of the magnetic field produced by this solenoid. And we can say that H is calculated by the formula I/N over L. Now in this case, I is the current carried by the solenoid, the coil, and we measure that in amps. N is the number of turns of the coil. And finally, L is something called the length of the flux path. Now, in the case of the solenoid in question, we can approximate this to roughly the length of the solenoid. So I'll just call that length, and it's measured in meters. So the unit amp turns per meter is reflective of this formula, really, because we're measuring I for amps, N is the number of turns, and L is a length in meters. Let's have a go at a quick example of calculating the magnetic field strength of a solenoid. And let's say that we have a solenoid that is carrying a current of 2 amps. So I'll just make a note on the side there, 2 amps. And let's say that it has 100 turns. And it has a length of 5 centimeters. So let's put those values into our formula and see if we can calculate a magnetic field strength. So first of all, I is 2 and N is 100. So I can say 2 times 100 over L. And we said that L is 5 centimeters. Now again, we should be using our standard unit of length, which is meters, in our formula. And the length given is 5 centimeters. And so we have to convert that into meters. So 5 centimeters is 0.05 meters. And if I calculate 2 times 100 divided by 0.05, we get an answer of 4,000 amp turns per meter. I hope you found this video useful on how solenoids are used to create magnetic fields, and then finally how we can calculate the magnetic field strength of a solenoid.